The topics for this webinar, as I mentioned, the topic is Introduction to 3-Axis Machining. We'll be going over what is 3-axis machining. We'll be starting with that. What is 3-axis milling? We'll be talking a little bit about part orientation and setup and how do you actually do that in our systems to get ready for 3-axis milling. Talk a little bit about machining workflow, what we think is the standard workflow that the people use with our products, and that would be the recommended workflow for you as well. And then programming considerations, a little bit different from 2-axis, so we'll be going over some of those specific to 3-axis. And then talk a little bit about the common machining strategies that people employ for 3-axis milling, like Z-level roughing, Z-level finishing, and parallel finishing. And finally, post-processing. So these are the topics we'll be going over. And I think we're in the demo portion of the webinar now, so it's all yours.
Thank you, Joe. Hello, everyone. Good morning, good afternoon, or good evening to you all, folks. And thank you again for joining us for our AMS webinar series for this month. We will be covering the Introduction to 3-Axis Milling topic in today's webinar. And we will cover first, we'll try to learn about what is 3-axis milling. So 3-axis milling, or 3-axis, refers to the 3 linear axes. So the 3 linear axes are the x-axis, which typically runs left to right, the y-axis, which runs front to back, and your z-axis, which goes up and down. So when you have parts that could be sculpted, that could be prismatic, where you need to move all 3 linear axes to be able to machine the part. So we would require 3 linear axes, so it's called 3-axis machining. Now, in this 3-axis, we have several different types of strategies for machining, and we will be covering them during our demo. So 3-axis refers to 3 linear axes, the x-axis, which runs typically left to right, y-axis runs back and forth, and then the z-axis up and down. So if you take a look at this slide here, you'll see that the x-axis is represented by the red arrow, the y-axis is represented by the green arrow, and then the z-axis is typically represented by a blue arrow, as you can see right in this slide. So you will basically, the cutter will be moving in all 3 axes simultaneously, all 3 linear axes to be able to produce a resulting machine part when you program it using our CAM products. Now, the next thing we will be talking about is for 3-axis machining, how we would be orienting the part and how we will go through the setup process to be able to program these parts using 3-axis machining. Now, to demonstrate this, I will switch over to our CAM product. I'm going to be primarily demoing the RhinoCam solution today. So we'll switch over to RhinoCam, and we'll talk about how we can orient the part and prepare it for machining. So as you can all see on the screen here, I have a solid model. It is a casing for a hair dryer. You can see the core part of the mold design that has been modeled. And this could have been either modeled in your CAD system, which could be Rhino. It could have been imported into Rhino in one of the several different CAD formats. So once you have the part imported and loaded, and the first step we want to make sure is we are programming in the correct units. So the first thing I would check is go ahead and take a look at the units. Typically, it is represented in the bottom of your screen in the status bar. It shows inches. So if you'd like to program the part in inches, you wouldn't have to switch or scale the units. If you'd like to program the part in millimeters, you can right-click on the units and go to unit settings, and you can change the model units from inches to millimeters, or if you need to switch it from millimeters to inches. So once you have established the model units, the next step is you want to make sure that the part is in the correct intended orientation for machining. So as we take a look at this part, either from the perspective view or looking down from the top view, we would like to make sure the part is oriented correctly to be able to fit the work envelope of your machine tool, plus it's oriented in the correct direction for being able to mill the part. So looking down from the top view, we can see all of the freeform and the sculpted features on the model, and this is the direction we would like to mill. So the z-axis is normal or perpendicular to this planar face that you're looking at here on the model. So that would be the orientation you would like to mill it from. Now, if you need to rotate the part to fit the work envelope of your machine, you could orient it using several different tools that are available to you, either using the CAD tools that are built into the host CAD system. We can select the geometry and use the rotation command using the gumball. We can rotate it. I can rotate it by 90 degrees. If the part needs to be oriented, so the length of the part needs to be oriented along the y-axis, or if you need to rotate it, if the part needs to be flipped over, we can also handle that. Now, what I'm going to do here is bring in another example. We'll talk about how to orient the part. And I'm going to switch over to another example in here to talk about orienting the part. So consider that you were provided a part from one of your customers, or it was designed in a different CAD program. And as you can tell here, the part needs to be reoriented because the part is not oriented in the intended direction for milling. As you take a look at it looking down from the top view, or take a look at it from the perspective view, you will notice that the part is not in the desired orientation. So which means we need to rotate the part. This could have been modeled in SolidWorks or any other parametric system where the top plane is not XY, the top plane is typically X and Z, or could be modeled in the Y and Z plane. So we need to rotate the part. So there's a couple of ways how you can orient it. You can use the CAD tools available in the CAD system to rotate it by using the gumball, or you can use the rotate command, and you can rotate it by 90 degrees to orient it. That's one of the ways to do it. The other option you could use is basically in the machining browser. You can go over to the program tab and go under setup and select orient part. So once you choose orient part, you have different ways to orient the part. In this particular example, I would like to orient it so that what you see currently along the y-axis needs to be normal to the z-axis. So you can actually select this arrow that points to the direction you would like to orient it, and then selecting OK will automatically orient the part. So if you now go back and take a look at it from your top view, you'll see that the part is oriented in the intended direction. And in the next step, we can move the part to the origin. You can select the entire part. You could use transform move, and you can pick one of the corners of the part and move it to origin by typing 0. So if the part is not in the intended orientation for machining, we would first use the transformation tools either in the CAD system, which could be Rhino or it could be Visual CAD, to orient the part. And then you can also move it to the origin using either the tools that are available in the CAM, or you could use the tools that are available in the host CAD system. Now let me go back and switch back to the part that we were working on here. So once we have the part oriented, we are now ready to set up the part for machining. So this would involve defining the number of axes. So we would go into the machine tool setup, and we would set the machine type number of axes to 3 axes. And then you can make the selection for your post processor in here. So I'm just going to pick a standard FANUC post, set the output file extension. And in the next step, we would like to define the stock material. So as you can see, we are working our way from left to right as we're working through this group in here. So stock, we could define the stock as a box stock. So when you define the stock as a box stock, the system will automatically identify the minimum stock that's required based on all of the visible geometries that you have imported or modeled. So the length is 8 inches, the width is 7 inches, and the height is measured as 1.94. So I would like to start with a stock That would be 2¼ inch thick. So I'm going to define the stock height to 2¼ click OK to accept it, and I can display the stock visibility. And now you'll notice that the stock is visible on top of the part, and you can view it from different views. The front view, you will notice that it shows there is stock being left above the part, and if you take a look at it from the top view, the XY extents of the stock and the part are exactly the same. It's 8×7, so it's flushed with the extents of the part geometry. If you need the stock to be larger in X and Y, you can define those parameters in the box stock, where you can change the length, width of the stock in addition to the height. Now, once we've established the stock, we could choose align the stock to the part. So I'm going to pick align. And in this particular part that we're going to be working on, the core of the mold, since the bottom of the part is flat planar and on the top of the part you have sculpted surfaces, I would like to flush the bottom of the stock to be flushed with the bottom of the part, so we have enough material being left on the top of the part so we can remove the material from the top. Now you could also align it to the center in the Z if it requires machining from multiple sides. So in this particular example, we would just want to have it flushed with the bottom. So the bottom of the stock is flushed in line with the bottom of the part. And for the XY, I'm going to leave it as center for the XY alignment. So it is centered on the part in X and Y as you view it from the top or the perspective view. Now, once you've aligned the stock to the part, in the next step, you can choose the material that you're going to be milling out of from the material list. So I could choose aluminum 6061. You could pick a different material type from the list. And this list can also be customized. Selecting material texture visibility applies the texture of the material to your stock. And you can toggle the visibility of the texture by selecting material texture. Now the next step we're going to do here is establish the XYZ origin for machining, which could be your work zero or called the program zero. This could be done in several different ways. Now, one of the ways I would like to do here in today's demonstration is use work zero. So selecting work zero allows you to specify the location of your work coordinate origin or the program origin. And I can set this to the stock material. I'll pick the zero face to be the highest Z, which is the top face of the stock. And for the zero position, I'll choose southwest corner. So we are establishing the XYZ origin at the top of the stock and the southwest corner. So selecting generate places the XYZ origin right at the top of the material. So when you place the workpiece on your machine tool and establish your 000, your touch off point would be the top of your stock material and the southwest corner. So you'll notice in this particular example, the XYZ origin for machining is set to the top of the stock material. Your world coordinate origin still remains for the part design at the bottom. Now, if you prefer to maintain the same origin for both the CAD world origin and the machining origin, instead of using the work zero, you could use align set world coordinate system, and you can move the stock and the part to the same location as we've discussed in one of our earlier webinars. So you could use set to stock, you could do higher Z southwest. This will transform the part and the stock to the same origin location. So we've defined the part, we've established the orientation, we've also created our stock and established the work zero for machining. Now, let's take a look at what our typical machining workflow would look like. So I'm going to go ahead and switch back to our presentation slide in here. So a typical process in 3-axis machining would be to load the part and the stock, which we've defined. And then we would start by creating roughing operation so we could remove the bulk of the stock material to bring it as close as possible to the net shape of the part. So program roughing operation in 3 axes. So once you generate a roughing operation, you'd want to run a cut material simulation to simulate the material removal. And then once this process is done and you're happy with the roughing results of the roughing toolpath, you can start out with a pre-finishing operation. This could be done using one of several different methods, and we will be covering a couple of different methods in today's webinar for pre-finishing. And then simulate, perform a cut material simulation. And then once the pre-finishing is completed, you can run a finishing operation. And again, we'll be discussing the different finishing techniques. We'll be covering both parallel finishing and Z-level finishing operations in today's webinar. You can perform cut material simulation for the finishing operations. Now, once you're happy with the result of the roughing and the finishing toolpaths, the last step is to output the toolpaths to the machine. We do this by calling post-processing to generate the output to the machine tool. So now let's go ahead and take a look at some of the programming considerations for machining in 3 axes. Now, the part that we have here is a solid model. Now, what are the types of parts that can be programmed in 3 axes? Now, we could work with solid geometries, which could be made up of, a bunch of surfaces stitched together would be a poly surface. In this particular example, you're seeing that this is a poly surface where multiple surfaces are joined together, which forms a closed, it could be a closed poly surface, or it could be even an open poly surface. You could program 3-axis toolpaths for geometries that are both closed or open poly surface. And we could also generate 3-axis toolpaths for just surface geometry. So if I go ahead and explode this, it basically explodes a poly surface into multiple individual surfaces. So we could generate toolpaths for surface geometries. Now this could be, you could also be importing geometries, surface geometries in the form of IGES files into your CAD system, which could be Rhino or Visual CAD CAM, and generate toolpath. So to generate 3-axis toolpath, you either need a solid model, a surface model. We could also work with mesh geometries. A mesh geometry would be like an STL or an OBJ file that could have come from a scanner, or could be come from a different sources. You could have generated a mesh geometry. So I'm going to bring in an example of a mesh geometry here. This is an STL file. As you can see, it's made up of triangulated data. So it could be OBJ. So basically, meshes are made up of a bunch of triangles, and you can see all the vertices in here. If I go ahead and display the mesh edge wires, you'll see each of those triangles, the meshes. So we could generate 3-axis program toolpaths for solids, surfaces, meshes. Now, sometimes users ask us, oh, I have a 3D wireframe geometry, and can I generate toolpath for that? So a wireframe basically represents a bunch of curves that could be in 3-dimension, 3D curves. To generate toolpaths in 3-axis, you will not be able to use a wireframe geometry. You need to have a solid or a surface geometry. So if you go into the 3-axis methods and select any of the methods in here, it's going to notify you saying no active part. So an active part requires you to have a solid, a surface, or a mesh geometry. Now, solid geometries, surface geometries, we talked about. Now, what are the different types of solid surface geometries we can work with? So we could, for programming 3-axis toolpath, this particular geometry that you see here has free form or sculpted surfaces. So you will need to move in all 3 axes to program toolpaths. Since you have a sculpted surface, now we can also program 3-axis toolpaths for geometries that are prismatic. Now, prismatic is something we looked at in one of our earliest webinars where we did some 2-axis toolpaths. You can also program 3-axis toolpath on prismatic parts where these are just straight extrusions where there's no freeform sculpted bottoms, no drafts, those are prismatic parts. So you could program 3-axis toolpaths on solid surface geometries that could be prismatic, it could be freeform. We could also be programming 3-axis toolpaths on mesh geometries as well. So pretty much you can even have a combination of mesh and solid surface geometries to program 3-axis toolpaths. So our CAM products gives you a wide range of abilities to program 3-axis toolpaths on solids, surfaces, and mesh geometries. Now, the next step here is we're going to take a look at how we're going to go ahead and program this part. So like we talked about in the machining workflow, the first step is to create a roughing toolpath so we can rough the stock out to bring it as close as possible to the finished shape of our part geometry. So to do that, I'm going to go over to the 3-axis methods and then select horizontal roughing. Now horizontal roughing is also called as known as Z-level roughing because it does roughing in levels. So in the horizontal roughing operation, you do not have to select any part regions or part surfaces. If you'd like to rough the entire part out based on the part and the stock that you define, you can skip the selection of part regions under the control geometry tab, select your tool for the operation, set your feeds and speeds, set your clearance, it's set to automatic. So we are working over from left to right as we work through each of these tabs in the roughing operation. Under cutting parameters, we specify the tolerances, the stock allowance. By default, roughing operation leaves 25,000 stock. So you want to then go back and do a pre-finishing and a finishing operation to remove the stock. You can change these parameters and values. You could choose the cut pattern, your cut directions, step over, cut levels, which is basically stepping down in levels, specify engage and retracts in any advanced cut parameters, and then pick generate. So selecting generate, the system automatically computes a roughing toolpath based off the part and the stock. And I've just generated the roughing toolpath with the default parameter settings, and you can view the toolpath in levels. Once it's generated, you can see each of these cut levels based on the step down, which is 50% of the tool diameter. So it's stepping down 1/4 of an inch for each pass. So I'm going to go ahead and switch to the simulate tab and run a cut material simulation to validate our roughing process. And at any time during the simulation, if you want to speed it up, you can use these simulation controls in the slider bar right below preferences. You could also choose pause and then pick simulate to end to run through the simulation. So as you can see in the cut material simulation, we've done a Z-level roughing. So roughing it down in levels. Also, you can see these stair steps. So roughing it down in different steps. And if I switch back to the program tab, you will actually see the part and the stock. You can toggle the visibility of the part and the stock. So the roughing process brings it as close as possible to the net shape of the part, and it leaves the stock that is specified to leave in the cut parameters tab. Now let's dive into some of these parameters in roughing and take a look at it. So the first thing I'm going to go in is to the cut parameters tab, and we'll talk about how the tolerance affects the toolpath. So as you take a look at this particular toolpath that we generated, if I step down to levels here, you can see that the slacker the tolerance that you've set, you're going to probably see that the deviation is within the tolerance, and you'll see, the chord segments, the toolpaths are much faceted in here. So the tighter the tolerance, you'll have much smaller chord segments, which maintain it within the accuracy of the tolerance that you specify. Now to illustrate this, I'm going to go ahead and switch back to our slide in here. And you can see the effect of machining tolerance. So a tolerance of 0.1 versus 0.01 and a tau. So basically, the slacker the tolerance, you'll have fewer chord segments, tighter. It'll make it more number of chord segments, and you can also fit arcs to the tool paths to by defining these arc fitting tolerances in the advanced cut parameters tab. Here's also an effect of the tolerance. You can see the in tol and the out tol, setting the tolerance to a slacker value versus setting it to a tighter value. So it makes it more accurate, tighter of the tolerance. I'm going to switch back to RhinoCam. So you can see the effect of tolerance right in here. We'll go back into the roughing operation and we'll tighten up the tolerance. I can tighten it to 1,000. So remember, when you tighten up the tolerance, you want to make sure if you're fitting arcs to your toolpath, you set your arc fitting tolerance to 2 times of the parameters that you specify in the in tol and the out tol. So we're setting it to 2 times, and then we'll pick generate. So once the toolpath is generated, this would result in much smaller chord segments, and you can see the toolpath, it's much more accurate, maintains it within a tolerance of a tau. So let's go ahead and run the simulation in here. And I'm going to skip by doing a pause, then selecting simulate to end. So we've now generated a roughing toolpath with a much tighter tolerance. Now there's a few other parameters we would like to talk about in the cut parameters tab. So we have core and cavity and core region. So what is a core region and what is a cavity region? So we have different cut patterns available for cavity regions and core regions in here. A core is like a core feature that is basically like an island or a feature that is sticking out on the model. So where the cutter can approach itself from outside the material and work its way in towards the part. So you can specify the cut pattern and cut direction and the step over for core features. So in this particular example, we have a core feature. So I'm going to set the step over as 40% for the core feature. And then if we had any cavities, this particular model, we do not have any cavity features. I'm going to give you an example of a cavity feature as well. And you can set the tolerance, you can set the cut pattern, the cut direction, and the step over for cavity features. So you can control the step over and the cut direction for core and cavity features independent of each other. So while the toolpath is being generated, I'll switch to a model to show a cavity feature. Now this could be this pocket in here would be considered as a cavity feature. Or if I go into one of the other files in here, I have the cavity of the same mold we looked at here. So this would be considered as a cavity feature as well. So for this, when you program a roughing toolpath, you would apply the cavity cut patterns that you have for the cavity features on the model. So core versus cavity. Now, if you'd like to apply a cavity cut pattern toolpath for the core feature, you can do so by clearing this checkbox. It says use facing cut pattern for core regions. When you clear the checkbox and generate the toolpath, this will apply the cavity cut pattern toolpath. So the cutter ramps in at the specified ramp angle, as you can see right here, and then applies a cavity cut pattern. So in this particular case, I'm going to go back and apply a core cut pattern and specify the parameters for the core cut pattern by selecting the core facing region cut patterns tab. The next important thing I would like to talk about here is the cut levels. So the cut levels is the distance in Z levels, so how much of material you would like to remove per pass in the Z. This could be set to a % of tool diameter, or you can choose a distance, or even specified by number of levels. And you can also contain the cut levels by specifying the top containment and the bottom containment as well, if you want to restrict the toolpaths in the Z. Engage and retract tab allows you to specify how you would like to ramp in for cavity regions, and how you'd like to engage for core regions to engage the cutter from the outside. And advanced cut parameters allows you to perform arc fitting, smooth cut connections, and cut rounding. So now that we have programmed our roughing operation, I'm going to go ahead and run a simulation here. Since we regenerated the toolpath after making these edits, you have generated roughing toolpath. We will go back and program a pre-finishing operation. So the pre-finishing operation could be done using several different techniques. In this particular example, we're going to talk about parallel finishing. Now, parallel finishing is a 3-axis method that can be used for both pre-finishing and finishing operations. And it's typically programmed with either a radius tool, which could be like a ball mill or a corner radius tool. Now, for the control geometry, if we do not select any regions or any surfaces, the toolpath will automatically be generated for the entire part region, entire part geometry that's visible. So I'm going to skip the selection of control geometry. We'll go into the tool. We'll pick a radius tool. In this example, I'm going to pick a ball mill. I'll pick a 1/2 inch diameter ball mill. For the pre-finishing operation, set the feeds and speeds to be loaded from the tool, clearance to be automatic, and over in the cutting parameters, we'll specify the global parameters. As you can see from the dialog, by default, the stock is set to 0. So if you'd like to do a pre-finishing operation, we would specify a stock to leave. So I'm going to go ahead and set this to 20,000. So I'm going to, remove these stair steps that are being left from the previous operation, which was a roughing operation, before I do a finishing. Now, parallel finishing method is a very ideal, great toolpath method for machining areas that are near flat or not too steep. It's a great way of finishing and pre-finishing on 3D models that are freeform or sculpted. Great way to generate toolpath, finish these features. Now the angle of cut, we'll talk about it in a moment. Step over control as well. So I'll put it as 20% and then select generate. So this creates a 3-axis parallel finishing, and the toolpath runs in parallel planes following the 3D geometry, as you see right here. So let's go ahead and run a simulation. I'm going to select play. So the stair steps that are being left from the previous roughing operation is being cleared, removed using a pre-finishing operation. We're using parallel finishing to accomplish this. So it just makes it easier on the cutter as you go from pre-finishing to finishing. Now the pre-finishing operation, the parallel finishing that we generated here, you will notice that when you run into vertical or near steep areas, even though we have a uniform XY step over specified, as you have these steep areas, it's going to leave more material in the steeper sections. This is the nature of how the parallel finishing toolpath works. So in order to be able to clear up this material, we would have to go back and program another parallel finishing operation by changing the angle of cut. So the angle of cut here is set to 0. 0 will run the cutter parallel to the x-axis going back and forth. So as you can tell here, the angle of cut on this particular parallel finishing operation is set to 0. So I'm going to make a copy of the same operation. We'll do a copy, right click and paste, and then double click to edit the operation out. I'll change the angle of cut to 90 degrees. I can set the stock to leave to 0. This could be our finishing operation, and then I can also tighten up the step over to 10% of the tool diameter and generate it. So setting the angle of cut to 90 will run the cutter in parallel planes parallel to the y-axis. So let's go ahead and run a simulation in here. And now this removes the scalloping that could have been left from the previous angle of cut, which was 0 degrees, which ran parallel to the x-axis. Here we're running it parallel to the y-axis. So to run through the simulation at any time, you can select pause and pick simulate to end. Now, since we have not selected any areas for machining like a containment region or part surfaces for machining, the tool path is generated for the entire part geometry. So to exclude and only machine around the areas where you have freeform and sculpted surfaces, you could select a machining region. The machining region could be a closed curve, which you could select under part regions. It could be a surface boundary, which could be a chain of, you can pick a surface and then, RhinoCam automatically extracts the edges, the boundary curves along the surface, or it could be selecting flat areas or even predefined region. Now in this particular example, I'm going to use select curve edge regions, and I'll pick this curve as the containment region and generate the toolpath. So selecting the curve as a containment region will basically limit the toolpath to the area that you specified. So it'll basically clip the toolpath to this region, and the region that you select can be parallel to your XY plane, and it could be anywhere along the Z axis. So we now picked a region. Now you can tell that by looking at this model, the toolpath is not getting all the way down on the side because the region I've selected, the tooltip stays to the region, so it's not offset further enough. So I can either, if I want to use the same tool, I would have to offset the region slightly towards the outside. I can do that in Rhino by offsetting the region slightly towards the outside and then go pick the larger containment region and generate the toolpath. Or if I'd like to choose a smaller tool, I can go ahead and swap it out. Instead of a 1/2 inch, I could swap it out to a smaller tool. So now simulating the toolpath, once it's generated, you will notice that the toolpath stays to the region that we've defined. Again, I'm going to choose pause and then go to end, simulate to end, to run through the simulation. Now that we have generated the pre-finishing and the finishing operation using parallel finishing, you will still notice that there are some sections of the model in the steep areas, there is still some scalloping being left. When you take a look at the part and the cut material simulation, you'll see this on these steep sections, you'll still notice scalloping being left. Now to be able to finish these sections, these steep sections, we have a 3-axis method called horizontal finishing, or also known as Z-level finishing. Now the Z-level finishing is great for finishing steep sections. For example, it could be like features like truncated cones when you have steep areas. So it'll basically step down in Z levels following the 3D model. So we'll go ahead and pick horizontal finishing. And again, if you do not pick any regions for containment, the toolpath will be generated based off the entire model. The most appropriate tools for horizontal finishing would also be like a radius tool, which could be a ball mill, or it could be a corner radius tool. So we'll go ahead and pick a 1/4 inch ball mill. We'll set feeds and speeds, clearance to be automatic. In the cutting parameters, we would set the cut direction. It could be climb, conventional, or climb conventional. We'll come back to these parameters and revisit them in a moment. Cut levels, you could specify your cut level containment. You control the step downs. Also, you can specify If you want to go all the way down in the Z to the bottom edge of the part, or if you want to restrict the toolpath, I could say I want to restrict it right up to this level, or I could even, enter in a value in here saying that I only want to go up to a certain height, and then pick generate. Will result in the horizontal finishing toolpath. So you're noticing here the toolpath generator is known as horizontal, or also called Z-level finishing, where it's generating constant Z levels. I'm stepping through the Z-level display, and as you can see, the toolpath display in levels. So this is a good technique to program steep areas in your 3D models, and this will go ahead and take care of cleaning up all of these scalloping that were left in the steeper sections on this particular core mold. Now I could go back in here to tighten up the step down under cut levels, generate the toolpath. It's a much tighter step down, Z-level finishing. Now we could also exclude some of these areas that were already finished using the parallel finishing by specifying cut level containment. So we can set the top containment, and I can lower it down, so I can choose where you want to begin the Z-level finishing or a horizontal finishing toolpath at. So it'll skip areas above this top cut level containment and only cut between the top containment and the bottom containment. So you don't have to go back and refinish areas that are already being finished using the previous parallel finishing operation. So selecting pause and simulate to end simulates to the entire process. Now the cut direction in horizontal finishing by default is set to climb conventional, which means it alternates between climb and conventional between each cut level. So if you take a look at this toolpath here, the first level does a climb cut, the next level does a conventional cut, and then it alternates between climb and conventional. So if you'd like to just cut in one direction, you could go back and set this under the cut parameters to climb only, and then generate the toolpath. Like how we could fit arcs in other 3-axis toolpath methods, we can also perform arc fitting in horizontal finishing as well by specifying the arc fitting tolerance and generating the toolpath. The arc fitted to the toolpath appears in dark blue, and the turquoise color represents the linear motions. And you can go back and make changes, edit the toolpath, regenerate it, and once you're happy with the result, we could go ahead and generate. The next step would be the post-processing. That would be the final step, and we're ready to output this to the machine tool. So to post-process the toolpaths, we would select the setup to post-process all of these operations to the machine. Right-click on the setup, and then select post. We'll post all of these to the selected post processor that you chose, and the posted output file will be displayed in your text editor. So this would be a typical workflow of programming 3-axis toolpaths. The same workflow would also work in our standalone visual CAD/CAM product, like how we demonstrated this in our RhinoCam product. Folks, if you have any questions at this point of time, I would be more than happy to answer them. Joe, is there anything else you would like me to cover
Yeah, we have to talk about post-processing.
Yeah, so we could post-process each operation individually based on the tool. If you do not have a tool changer, you can post them out to separate files, or you could post them all, right-click and post, right-click on the setup, or you can right-click on the machining job and choose post to post all of these into your posted output file. And it does output your tool changes based on the tool numbers that you defined in your tool library. You could also generate what is called a shop document. This would be come in very handy for creating a setup information sheet. And you can choose a template for your shop documentation. And this generates a setup information sheet, which would include information about your machining operations, the estimated machining time for each operation, the tools that were used, your feeds and speeds, and any comments, including the stock material and the stock dimensions that you put in here.
All right, well, a few questions have come in, and there was a question on, can you use just a single cut level for a horizontal finish and or roughing? So
Absolutely. So in the horizontal finishing, you could go to cut levels tab and you can set the number of levels. So I could pick the number of levels to 1, and I can also set the range for the top and the bottom. You can specify that here. I can set it to like 1.7 minus 1.73 to minus 1.74 generated. This would result in a single cut level for horizontal finishing. So the same could be done in the roughing operation as well. We could go into the horizontal roughing, go to the cut levels tab, and you could specify the cut level containment for the top, cut level containment for the bottom. I can pick the bottom containment here, and I can set the top containment, set the number of levels. I can change it to 1 and then generate it. Okay, so it says nothing to cut because I have a stock to leave in here. So I need to make sure that the value I put in for the cut level and the stock to leave is within the range. So I need to make sure that, and I can specify the bottom and the number of levels in here. So that's how we go about specifying the cut levels.
well, there was another question about feed rates. Can you talk about how plunge feed rates and cut feed rates work?
Certainly. So each operation, you have different feed rate controls. You have feed rate controls for plunge, approach, engage, cut, retract, and departure. So let's take a look at one of these toolpaths in here. So let's go to one of these levels. So as you can see from the toolpath that's being displayed, so the plunge motion is from your clearance plane down to just short of the approach. You can see the toolpath, the display of the toolpath that's appears yellow in color. That's your plunge motion feed rate. So whatever you specify in your cut parameters for the plunge motion feed rates will apply to that. And then you have your engage, approach, and the engage feed rates being applied in here. So since we're using a facing a core cut pattern, the cutter enters in, it's engaging in from the outside. So it goes from the plunge to approach to engage, and then you have your cut feed rate. And then when it retracts, it applies a retract and a departure feed rates. And then if you have set it to transfer using use rapid, it'll transfer out at a rapid feed rate that you've defined on the machine, which could be a G0. The rapid feed is defined in the machine, or if you set it to a set value, it'll output the set value for those feed rates. So these feed rate values can be defined in the operation, or you could be specifying these feeds and speeds in the tool, and you can save those feeds and speeds in the tool and then load those feeds and speeds into the operation from the tool automatically. If you take a look at a operation like a parallel finishing operation, again, you have the options to specify your approach, engage, feeds and speeds, and the entry and exit parameters for each of these can be set right in here. I can specify the length, angle. The same thing can be set for the length and angle, then generate it. So that would apply your plunge, your approach, engage, cut feed. The same goes with retract, departure, and then transfer if you program it in multiple levels. So likewise, we have control for the horizontal finishing as well. You could specify entry and exit for the approach, engage, retract, and departure motion, and set those corresponding feed rates in the feeds and speeds tab. So you have your plunge, approach, engage, cut, retract, departure, and the transfer feed. I hope that answers the question.
Can you talk about selection of post processors? There was a question on Thermwood posts. You can talk about where you can actually select the posts, and
Sure.
maybe even talk a little bit about the modification of posts.
Absolutely. So the post processor selection can be found by going into the set post processor options on the program tab. So as you can see where my cursor is, you click on post, and then in the current post processor, you select the drop down or the pull down menu and choose the post processor. Now these posts in here are either listed by name of the controller or the machine, or it could be a combination of the both. So I could go down the list here to select the Thermwood post. So we have various different posts for Thermwood 40, 91,000 series, C43, C45. So I can choose the post that's most appropriate. I'm just going to pick the C45 in here, for example. We can also set the posted file extension. It could be nc.cnc, or if it's expecting a different file format, you can always click on Add New and add the new file extension to the list, and then the list will appear. The file extension will appear in the list. So that's how we go ahead and select the post processor. If you need to make any modifications or changes once you've selected your current post processor, you can choose Edit, and selecting Edit will load the post processor generator utility, and you can go ahead and specify and make changes. So for example, if you'd like to output line numbers on each and every line of your code, you can toggle on use sequence numbers, which basically outputs your line numbers. If you need to switch the units for output in the post, if you want to output in millimeters, you can switch the output units to millimeters, so the output will automatically be scaled from inches to millimeters, even if you have modeled and programmed the toolpaths in RhinoCam or in VisualCam in inch units. And then you can make changes or make edits to the program startup code, tool chain sections. So each of these macros are defined here in the post. You can set the maximum spindle values that the machine is capable of handling. The high values can be set right here, and the feed rate, the max values can all be defined right in here. So once we have selected the current post processor, right click, and then selecting post will automatically output it to the current post that you've selected. Now you can also make a change to your post processor right at this step here. If you want to output it to a different machine, you can just go to the current post selection here and change it to a different machine tool. And then selecting post will generate the posted output file, and you can view it in your text editor. I hope that helps.
There was questions. Yeah, that should be good. There was a question on feed rate reduction factors. Can you talk about a little bit about that?
Certainly. So feed rate reduction factors can be specified under the Feeds and Speeds tab. They can also be set in the tool definition as well. In the Feeds and Speeds tab, we have feed rate reduction factors for plunge between levels. So plunge between levels is when we have multiple Z levels. So for example, in this case, you have multiple levels, and when the cutter is, you're cutting down, plunging down from one level to the next level, you can specify a feed rate reduction factor. So as it goes from, from the first level to the next level, you can specify to use a percentage of the cut feed rate for plunging between levels. So for example, if the cut feed rate in this particular program toolpath is 40 inches per minute, and I can set the plunge between levels to 20%, it'll apply 20% of the cut feed rate, so which would be 8 inches per minute as it goes from the first level to the second level as it goes down in the z-axis. That would be the plunge between levels reduction factor for feed rate. We also have a feed rate reduction factor for first XY pass. The first XY pass is when the tool is taking the complete width of the cutter on the first pass. So when we program a toolpath, the first pass, which typically if you're programming in a cavity where you have a pocket, so the first pass will be taking the full width of the cutter, so you can reduce the feed rate for the first XY pass by specifying a percent of the total cut feed rate. So that can be specified again in the feeds and speeds tab. For the first XY pass, you can reduce it down. Let's say if I put in 25% of the cut feed rate, the first XY pass would be 25% of 40, which would be 10 inches per minute. Now the bottom Z-level feed rate reduction factors applies primarily to profiling operation in two axes. So when you're profiling a part in multiple levels, so for example, if I add a two-axis profiling toolpath by picking this geometry in here, and in the cutting parameters, I'll choose to cut on the outside. We'll pick the cut depth and we'll step it in 100 thousandths per level. And when we specify a feed rate reduction of bottom Z level, I put in 25%, generate a toolpath. So the final cut level will be at 25% of your cut feed rate. So that's what the bottom Z level feed rate reduction factor would be. So you have 4 levels. The final level would be at the reduced feed rate that you specify under feeds and speeds. I hope that answers your question.
Yeah, we're getting close to the end, but there was a couple of questions on the G-code editor. So it seems like a lot of people are unfamiliar with that. If you can show where you can access it and how you can actually load a G-code program.
Absolutely, I'll certainly do that. So let me go ahead and generate this toolpath in here. I'll just leave the origin where it is on this particular part. I'll generate the toolpath, and I'm going to go ahead and post-process this output. I'll just pick a standard output. I'll just output it to, let's say we want to output it to mock. And there's our posted output file in here for the profiling operation. Now, the G-code editor can be accessed by going up to the CAM menu and then selecting G-code editor. So when you select G-code editor, there's basically overlays on top of your machining browser, which means the mill browser interface is now swapped out with the G-code editor interface. And then you can go ahead and load in your G-code output file that you may have just generated from your RhinoCam or VisualCam product. You select the file and then pick open, and that actually brings in your output file, the G-code file that you generated, and also previews it on your screen.
I want to interrupt here, and the G-code file doesn't necessarily have to be generated by RhinoCam or Visual CAD/CAM or any one of our CAM products. It could come from any external CAM product as well. So if you have a legacy system that you're using, or if you have a companion product that you're using, and you want to verify the G-code generated there, you can bring it into this product as well. Thank you.
Thank you, Joe. So once you have loaded the G-code, you can also bring in your tool library. So the tool can be used for performing the simulation. So I could export this back from the mill module. The tools can be exported. I can save this to a library pick a file format, and then I can switch back to the G-code editor module and load the library in here. So the tool is now loaded. You can define your stock material and then perform a simulation of the G-code output file. And in the editor, these are basically automatically color-coded based on the motion type, rapids, linear, arc motion. You can make edits to the G-code. You can also go back and rerun the simulation. And
yeah, this G-code, what you're seeing, the simulation is actually the simulation of the G-code file. It's nothing to do with the internal toolpath. So it's so you're basically verifying whether your G-code is correct or not. So that's precisely why we wrote this product, and we make it available to all AMS customers of standard and above. All right, well, I think we've come to the end. I think it was very informative, and we had a lot of questions, which is good. So as we mentioned before, we'll make this recording available to everybody, send it out in a day or so. And thanks for joining us. And if you have any questions or any additional questions related to sales or support, contact us. There's many ways to contact us. Email, you can go through Skype, or you can use chat. There's a chat window when you go to our website. You can use that. That's pretty convenient as well. So thank you again, and have a great day. And we'll see you in about a month. Take care.